Okay, so we're going to do page 333, number 13, and number 14. So number 13 is a parallelepiped is determined by the vectors OA, OB, and OC, is given here. First part is draw and sketch a parallelepiped formed by these vectors. B, determine the coordinates of all the vertices of the parallelepiped. Well, four of the coordinates are given, basically. So you've got the origin for each one of these, so the origin is going to be one of them. Point A is -2, 2, 5. Point B is 0, 4, 1. And point C is 0, 5, -1. So we've got four of them. We just need the other four. So first we have to draw this. And I'm going to jump right to my diagram of it, and I'm going to explain how I got this diagram. Okay, so page 333, number 13. First of all, we draw in the X, Y, and Z axes. Okay. Then we want to plot the vector which is OA, -2, 2, 5. So there's point A, -2, 2, 5. How did we get that? Well, I measured this all out in centimeters. So I went 2 centimeters back on the x-axis, so that's -2. And then I went 2 centimeters to the right, parallel to the y-axis, so there's the -2, 2. And then I went up 5 parallel to the z-axis, and that gives me the point there. So that gives me vector OA. OB is from 0 on the x-axis, so it doesn't move anywhere that way. And then it goes on the y-axis 4 units, and then it goes along the z direction 1 unit, so 0, 4, 1. And that gives me vector OB and point B. Vector OC is 0, 5, -1. So again, 0 on the x-axis, 5 on the y, and -1 parallel to the z. And that gives me point C and vector OC. So I've got OA, OB, and OC. Now to create the parallelepiped, we're using these as 3 edges of the parallelepiped. To make this bottom parallelogram, I'm going to take vector OB and add it to OC. So OB translates over here, and I'm taking OC, and that translates up here. Now I have a parallelogram here. That's actually the front face, because these two vectors, OB and OC, because the x-coordinate is 0, they're on the YZ plane. So they're actually right there on the face of this paper. Vector OA goes back 2 units in the x direction, so it's actually going into the page. Okay, so it's going downwards into that page, this one here. So this is the front face of the parallelepiped. And then I want one of the other sides, so I take this vector here, and OB, and I translate OA over to here. So I get one of the sides that you can see, one of the faces. And I take that vector and I translate it over here again, and I get another one of the faces. OB I put up here, so that this is a parallelogram shaped the same as this parallelogram. Okay, it's opposite face, that you can't see that face. And continue over here. So BE goes up there, which is the same as OC, BE, DE. OC is also AG. So you just keep going till you complete that parallelepiped. Okay. It took me a few tries to get it right, but so it does take some time. Now to get point D, E, F, and G, which I've labeled here, I'm going to show you two methods. Two methods except for point F, I have one method for point F. So method 1. Okay, method 1 is the equal vectors method. We know that vector OA is equal to vector BD. OA equals vector BD. So I write that down here. OA equals BD. Well, OA we know is negative 2, 2, 5. Okay. BD is OD minus OB. That's our formula for a point-to-point vector. OD is what we don't know. OB is 0, 4, 1. So at this point, we want to get rid of this so that we can solve for OD. Add 0, 4, 1 to both sides, and you get OD equal to negative 2, 6, 6. Now OD is just a vector. We want the vertex, so then we have to make another statement. Therefore, D, which is the vertex, is at negative 2, 6, 6. Okay? And you can do that for all of the vectors in all the points in this diagram. Okay, so you can say that OA equals CG. You can say that OB equals CE, and so on. And once you've got G, you can do OB equals GF, and you'll get them all that way. The other method is the parallelogram law. Okay? So in the parallelogram law, if we look at this parallelogram here, formed by O, B, D, and A, if I join the origin to D, that gives me vector OD. Now, OA plus OB using the parallelogram law equals OD. Okay, so OA plus OB using the parallelogram law equals OD. So I'm just going to write that down here. So OD equals OA plus OB, as we just looked at. Now we can just substitute in what those vectors are. We know them. Okay, so substitute them in, combine them, and we get that OD equals negative 2, 6, 6. Therefore, the vertex D is negative 2, 6, 6. Okay. Same process will work for E and G using parallelogram laws. And a quick method for getting vector OF, well, let's take a look at the diagram here again. From the origin to point F is going to be OA plus OB along here, and then plus OC along here. OA plus OB plus OC gets me OF. Okay? So that's the last one. OF equals OA plus OB plus OC. And you can work those out. The next question was question 14. So question 14 on page 333 is this one here. Given the points A, 2, 1, negative 2, 1, 3, and B, 4, negative 1, 3, determine the coordinates of the point on the x-axis that is equidistant from these 2 points. So the same distance. So let's write this down. Okay, we've done a question like this in 2 dimensions, but in 3 dimensions, let's see what it looks like. So PA00 is going to be the point on the x-axis. If it's on the x-axis, the y and the z have to be 0. So the point has to have these coordinates, A00. We're going to let that be point P. And the distance from A to that point must be the distance from B to that point. Okay? So we know that AP magnitude equals BP magnitude. They're not equal in vectors, but their magnitudes are equal. From that, we can write this statement, OP minus OA. That's how we do a point-to-point vector. Okay, BP is OP minus OB. We want the magnitudes of both. Plug in the coordinates. Okay. Simplify it. And then plug in our formula for the magnitude of a three-dimensional vector. Okay? We've got this. So x coordinate squared, y coordinate squared, z coordinate squared. Same here. Now if we want to get rid of the square roots, we can square both sides. If you square both sides, you get this statement. I've also squared the -1 and the -3 in these. The 1's go away, the 9's go away because they're the same on both sides. So you end up with a plus 2 squared equals a minus 4 squared. Now if you're going to square root both sides here, you got to remember this is like a difference of squares. Okay, so you can't just write a plus 2 equals a minus 4. A plus 2 equals a minus 4 is actually going to give you no solution. But what you could do is do a plus 2 equals plus or minus a minus 4 and solve it. If you use the plus, you're going to get no solution. If you use the minus, you're going to see that a is 1. The other method that I used is I expanded them both. Okay, so I get a squared plus 4a plus 4 in that one. A squared minus 8a plus 16 in this one. The a squareds go away, you can cancel them out on both sides. And you end up with 12a equals 12 and a equals 1. Okay. And since you got a equal to 1, the point on the x-axis is very nice. It's the point 1, 0, 0. And that's it for those questions.